Swayam Prabha. Digital India. Educated India.
Hello friends, so far in this course we have seen how to measure different deflection of control surface, how to calculate center of gravity, and all these experiments required different sort of sensors to be either calibrated or recorded, and the software which we used was LabVIEW. Now for all this sensor data collection we used a module, an IDAC card we used. Now today what we will be concentrating on how these sensors work and how do we get or collect data using this sensor. Before this lecture we used an IDAC, but for illustration purpose or demonstration purpose we will be using a processor board, that is Arduino Uno, and MEMS sensor, that is micro electromechanical systems, and the code will be using Arduino IDE, or you can use any other software such as C++ or MATLAB, any platform which you want, you can write that code. So today's lecture will be basically on various type of sensors and their working principle and how do we collect data from them. So different sensors which we will be discussing will be: first, pressure sensor. Now these pressure sensors usually are used to calculate your altitude and airspeed. The second sensor which we will be concentrating are accelerometer. Third, rate gyro. We will be seeing what is the importance of magnetometer. Then we will see how angle of attack sensor works, and why it is needed. These were the sensors which you saw in flight data recorder. While we showed you the data collection of flight data recorder, you saw what were different total pressure and differential pressure, what were the acceleration in all three axes, what were the roll, yaw and pitch rate for different axes. We did not mention this magnetometer, but instead of that we mentioned what were your roll angle, your pitch angle and your yaw angle, and we mentioned angle of attack as well as side slip angle. Plus in FDR we also saw the result of control surface deflection, that is deflection of elevator, deflection of aileron, deflection of rudder. These were the data we saw in flight data recorder, excluding your magnetometer data and your GPS data, which will be our sixth sensor which we will be concentrating on. So let's start with your first sensor, that is your pressure sensor. Now as I already told you that pressure sensors are used to calculate altitude as well as airspeed. So first, altitude. Now the general equation used to calculate altitude is a simple hydrostatic equation given by P2 minus P1 equals to rho g Z2 minus Z1, where Z2 minus Z represents your depth in case of fluids. This is your density, and this is pressure with respect to position 1, position 2, position 1. Now in case of height, just you have to substitute, instead of this depth you have to substitute it with altitude. So the equation will become P at particular altitude minus P, that is pressure at ground, equals to rho G H minus H ground. This is at particular altitude and this is your ground. And these values, that is H altitude and H ground, are with this, that is height above sea level, which will give me, this will be with minus sign, because in case of fluids the depth, that is positive z direction, that is depth is downwards, this is known as positive z, whereas in case of height we calculate that above sea level this is negative z, hence we get a negative sign. Also you can see that as altitude increases this value will decrease, so overall equation will be positive. Don't get confused why we are using my negative sign and not negative sign here. Now in this all calculation, one thing we approximated is that density remains constant for all height, or here. In case of water or any fluid, you can approximate that density remains constant as you go beyond a certain depth. As height increases, your density decreases. So if you want a more accurate result, you have to incorporate the changing density as the height increases. So density with height is given as change of density, that is rho h, equals to rho naught, that is at sea level, into T temperature at particular height by temperature at sea level to the power of n plus 1, where n is equal to g naught a into r. Now g, you know, this is acceleration due to gravity, a is your lapse rate, that is minus 0.0065, and this is your gas constant represented by R, which is equal to 287, and the temperature T naught at sea level is 288.16 Kelvin. Now using this approximation, you will get exact value of density at that particular height, that you can substitute in this particular equation. The output which we get from digital systems are always in terms of voltages or in terms of current. That's why the output which you will be getting will be something in terms of voltage, that we have already seen in case of previous experiments where we calibrated your deflection of control surface, and the output which we were getting was in terms of voltage. So we have to calibrate that, and output, for instance, for this something pressure absolute will be in terms of, say, P ground minus P altitude plus some noise, which is equal to rho g, and these both are above sea level, so you get h, that is altitude above sea level, ASL, plus some noise. Now this is for calculation of altitude. Now as the second application of pressure sensor is to calculate airspeed. Now the principle for calculating airspeed and altitude is same. The difference between them are, for altitude, block diagram is as follow. You have a chamber which is divided into two volumes by a small diaphragm. Here you have a standard pressure, some known pressure you have there, and this vent is open. This vent is open for ambient air. So the pressure difference here, P, pressure difference between these two volumes will cause a deflection in this diaphragm, which will be again given to you in terms of voltages, which can be calibrated, and you get what will be your present altitude based on the pressure which you have got. We have already shown you this will be your output. Something relation will be the difference between your pressure at ground and particular altitude plus some noise part will be there. You can, if your instruments are quite accurate, then noise can be neglected, but we generally consider some noise part here. And the difference between these, this was for altitude. For airspeed, you have a pitot P1 and P2 are the volume chambers. This is same diaphragm. Now it has two outlet. One is at the front. This will be open to your airflow, which will give you total pressure, and this is a small vent here which will give you static pressure, P static. Now this will compare with respect to your total pressure, you will get a pressure P1 on left volume, and due to static pressure you will get pressure on right volume. The difference between these two pressure will result in giving a deflection to your diaphragm, which again will give you a voltage compared to that deflection, which can be again calibrated, and the difference between these two pressures can be noted in terms of voltage. And the relation which goes for calculation of airspeed is P2 equals to, this is P total, this is P static. So this will be P total equals to P static plus half rho V A square. That is, this is VA is a velocity of dot ambient air. So this is a basic difference between your pressure sensor for airspeed calculation and your altitude calculation. This is a basic difference between the block diagrams. The second sensor which we talked about was accelerometer. Remember when we showed you the flight data recorder, you saw there were three terms named as AX, AY and AZ. These represent acceleration in X, Y and Z direction. Now accelerometer, the working principle is, this is for MEM sensors. MEM sensors which you use can give, the schematic of that will be, these are your this is your proof mass. These are your springs, these and these are your springs. These all are fixed plate. Now, when the body is in acceleration, this proof mass oscillates. For suppose this the velocity or acceleration is experienced in this particular direction, your proof mass will oscillate in this particular direction. These are with spring constant K. So the capacitance between these plate will change, and corresponding to that capacitance you will get a voltage. These voltages when calibrated will represent your acceleration in particular direction. Now since this proof mass can only oscillate in one particular direction, so for 3 axes you have to have 3 different accelerometer for 3 different axes, that is x, y and z. Each have a different accelerometer that can move only in particular direction. This proof mass will move only in x direction, for y it will move only in y direction, and for z it will move only in z direction. And based on that change in capacitance is C1 and C2, you can calibrate that to get what will be the required voltage and what will be the acceleration of that particular accelerometer. Next sensor which we will be discussing will be rate gyros. Now in rate gyro, the force which you experience is due to Coriolis acceleration. Coriolis acceleration. That is, suppose you have a body which is moving with velocity v, and when it is subjected to an external rotation, or you can say angular velocity, it will experience a force which will be perpendicular to your axis of rotation and velocity. That is, it will experience force in this particular direction. You can name it as force, or in this particular, suppose this is x direction, then this will be acceleration in x direction or force experienced in x direction. Now once this force is experienced, now the circuit will be the phenomena or the principle behind calculating what will be the voltage corresponding to this angular motion, what will be the force, that you can calibrate. The principle will be same. Acceleration, the acceleration experienced will move the proof mass, and the proof mass will vary your capacitance, and according to that capacitance you will get a voltage. The block diagram for this is little bit complex, corresponding to acceleration. Here acceleration is different because this is due to Coriolis force. The block diagram for this is, or a schematic for, rather I can say a schematic for rate gyro is, this is These are fixed plates. This is further mounted inside a casing. Which is and similarly this will be symmetrical in about this axis, and this is all mounted on a plane. The working of this is a schematic of rate gyro. Now when the body is not rotating or it doesn't experience any angular velocity, the movement will be with this. Suppose your body is moving in this particular direction, so your outer casing will be moving in that particular direction, that is oscillation will be in this particular direction, either this or this outer case will be moving. Once it experience angular velocity, say about this axis it experiences angular velocity. Now this particular inner casing will be moving. These are fixed plate, as you know, so this will be moving in this particular direction or oscillating in this particular direction. This will result in change of capacitance between these plates, and as I already told, due to change of capacitance you will get a respective voltage, and that you can calibrate to get what are the rates in X, Y, Z, that is roll, pitch and your rates.